So the next scene will probably be all 100 capacitors mounted. And there it is, all 100 capacitors mounted. Zoom in, get a good look at them. I believe I'll go ahead and turn the light on. Get even a better look. That's 100 of them. Next, I'm going to charge one and give a demonstration of the discharge effect of just one by itself. I've done calculations that will show that each capacitor is capable of a 200 amp, well actually in excess of 200 amps of pulse discharge current. So the next scene we'll do the single capacitor, we'll charge it, then we'll discharge it into a short, and that's what we'll do. Using the capacitor charge discharge box, first I'll do a charge cycle, then I'll do a discharge cycle. The capacitor is connected properly and works properly. Now I'll charge the capacitor, put it in the free floating neutral position. Now we'll show a discharge. I'll take the screwdriver, take this screwdriver and short the capacitor. Pretty hefty pop. That's 200 amps, a little over 200 amps of pulse current. We have 100 here, so I'm calculating we should do about 20,000 amps of pulse current. Pretty serious discharge. It'll have to be done outdoors for safety reasons. This is the mathematical process of figuring out the amount of peak discharge current of the 1000 microfarad 200 volt capacitor. First we have to find the impedance of the capacitor, and the impedance is the capacitive reactance X sub C plus the resistance R. A simple and practical way to do that is to use a test circuit with a 60 watt bulb in series with the capacitor. You apply AC to the capacitor at about 1/2 of an amp, and a 60 watt bulb is very close to half an amp. So we plug this circuit in and we measure the voltage drop across the capacitor. For accuracy, we take and we measure 10 capacitors and we average the voltage drop, and we find that we had a voltage drop of 1.2 volts, 1.24 volts RMS was the average between 10 capacitors. So to determine the impedance, or in this case resistance because Ohm's law works for both, we measure the voltage drop. We divide E, the voltage drop, by I, the current half an amp, and we come up with an average of 2.48 ohms. Now to get an idea of the ratio between the effective series resistance, which is the loss factor of the capacitor, the ratio between that effective resistance and the impedance of the capacitor, first thing we did is we used the formula to calculate what the impedance of a capacitor would be if it were 1000 microfarads. And by using the formula we got 2.65 ohms. And that's higher than the actual impedance that we were measuring. Now the reason for that is that the electrolytic capacitors are most often used in ripple filtering and in signal coupling applications where excessive capacitance has no undesired effect. And on the opposite side of that, capacitance less than the rated value causes suffering in performance by allowing higher ripple voltages and low frequency response to suffer in coupling applications. So electrolytic capacitors by convention are made to the tolerance of minus 20% on the low side to plus 100% on the high side, and therefore I used an average between those two extremes of about 1500 to be more like the original and actual value of the capacitor. So the average 1000 microfarad capacitor is really closer to about 1500 microfarads. So by using the formula and assuming a value of 1500 microfarads, we come up with a conclusion that the resistance is about 0.71 ohms. Now capacitor charged from 120 volt AC house current rectified will reach about 167 volts. And at that voltage, the current can be found by dividing the voltage let's see what we used. We used 150 volts, and our actual discharge current will be higher. Even at 150 volts divided by 0.71 ohms, we find that we have a discharge current of 211 amps. So peak discharge per capacitor is over 200 amps. And therefore at 100 capacitors in parallel, assuming that the wiring has low enough resistance, and in this case I'll use 12 gauge for bus and 18 gauge to wire each capacitor to the bus, I'll have 12 buses. I should produce very near the calculated value of 20,000 amps of discharge current. July 11th, 2002, approximately 9 p.m. Let's make that about 9:11 p.m. Central Standard Time. And not only have I spent approximately 25 to 30 hours wiring this creation, 100 of these 1,000 microfarad capacitors in parallel, I've also given this I did indeed produce the buses, 12 number 12 wires for buses. We have the back 7 of each row on one bus by themselves, and then the front 10 on another bus. And of course we only have the front 9 on the center 2. We allowed space for the terminals, and the 17 per row for 4 rows, and then 16 per row for 2 rows, made us have exactly 100 capacitors. 100 times 1,000 microfarads at 200 volts. Probably about 20,000 amps discharge current, because I see very little opportunity to increase resistance in the wiring or even very much impedance if we should produce a short duration pulse waveform. In any event, because of the size of the wire and the short distances, I think we'll come up with pretty close to 20,000 amps. And on each capacitor is wired to the main bus with number 18 wire, but the length on each capacitor's wiring is only about 1.5 to 3 inches, so we have pretty low resistance involved here. My first experiment will be performed outdoors. I've taken a piece of bare 12 gauge wire and made it into a T shape using another piece of 12 gauge that's insulated to form a handle or a means of support. And what I'll do is outdoors, of course, I'll discharge the capacitor like this, and I'll do the experiment to determine if the 20,000 amp peak current will last long enough to blow the wire into, which should make a very loud explosion noise. And of course the 12 gauge wire, being as large as it is, will make a rather loud noise when it goes, and it'll probably throw pieces of molten metal. So it'll be absolutely critical that this be done outdoors. I'll tape it to a piece of wood, a 1 by 2 about 50 inches long, and I'll do it from a safe distance. So that will be the first victim, or the first experiment. This is the setup I'll be using. We're set up outdoors and fully charged.
Wow!
Wasn't that enough? Made my ears ring. Whoa. Oh, you should have been here. You should have been here. Oh, the whole thing's hot. It didn't even use up all the charge. Yeah, let's see if I can blow it too this time. Blew it in two? No, I didn't. I can't blow it in two. I can get it pretty hot though.